Uh, so first of all, Dr. Amit, I welcome you in this webinar, and we are very privileged that you have accepted our request and you find out some time to give to share your thoughts and deeds on microwave and metamaterials. And I would like to request Professor Abdullah, who is the chairman of the Internal Propagation Society, Kerala chapter, to say a few words, and then we will begin the session. Professor Abdullah, what to you? Hello, Professor Abdullah, are you? Professor Abdullah, can you hear me? Okay, so I think he is not here. So let me formally introduce our speaker today. So Dr. Amit Kumar Singh is currently working as an assistant professor in the Department of Electrical Engineering, IIT Jammu. He worked as a postdoctoral researcher in Korea Advanced Institute of Science and Technology, Republic of Korea, from November to February 2020, November 18 to February 2020. Now, he did his PhD from Indian Institute of Technology, Delhi in 2018. Dr. Singh has co-authored or co-authored over 30 international journals and conferences. And also simultaneously, he is the reviewer of many renowned IEEE journals and transactions. In addition to that, he also got some awards, very prestigious awards, including that he is a recipient of GORS 2019 Fellowship by Global Center for Open Research, that is in KAIST, South Korea. And his current research interest is metamaterials for 5G and future communications, millimeter wave high gain beam steering antennas, and many more. So Dr. Singh is currently looking for some self-motivated researcher to work with him. So after the presentations, after listening his talk, if any participant is interested, they can directly email to him. I will give his email ID in the chat box. So later one can email to him for further interest. So with this, we are again very happy, Professor Amit, to accept our request to share your work with us under the umbrella of IEEE Antenna Propagation Society. And with this, I think the stage is yours. Professor Amit, you can start your presentation and your talk.
Thank you, Professor Sukumalde, for such a nice introduction and just introducing with the audience now. So I welcome all the audience for my talk as well. And as Dr. Sukumal introduced that today we are going to have a talk and that talk we are going to have on microwave metamaterials for future communication applications. So what exactly the word future communication means is that is what in the future generations, what type of communication medias we are going to look for. And that is not just for us. Whenever we are saying a communication system, that includes us as well as all the devices which is going to communicate in future. That is something called as communicating devices as well. As we know, in coming future, all the devices are going to communicate each other. That is something called as IoT based devices. So whenever we have such kind of devices, then requirement as well as bandwidth, speed, accuracy, and many such things also becomes very, very, very important for us. So that's why the topic here to discuss is how we are going to use microwave metamaterials for future communications. So Here we are going to start our talk. This is just my research interest, which Professor Day just he told about. I work regressively on metamaterials for 5G and future communications, that is 6G. Millimeter wave high gain beam steerable antenna design, massive MIMO antenna for 5G and beyond, deployable high gain antenna for CubeSats and microsatellite applications. And one of the interesting, actually very interesting topic on which we started recently working is microwave imaging for biomedical applications. This involves really pretty good applications in coming days, as well as at the present day of this COVID-19, as all of you know that in which what kind of pandemic condition we are facing and what are the different solutions we are going to have. So further details of the research can be found on the given website link, which I am just displaying on the this slide downward. Now, for today, this is the outline of my presentation. Whatever we are going to discuss, that is the fundamentals of metamaterial, advanced level metamaterials and its applications. What exactly 5G, that we call it as future communication system, is, and also we are going to discuss about some of the major aspects of 5G, that is the basic requirement. Whatever we people are working, is it 5G or not, or just kind of some kind of hit and trial type of method that people are doing. Now, followed by, I will also try to discuss some kind of millimeter wave antennas, and also we will try to go for material based millimeter wave antennas where I worked. And uh, in terms of 5G in South Korea, Seoul, about a few months back, about 7 or 8 months back, when Koreans were testing this 28 gigahertz band and 38 gigahertz band of the 5G, I have been one of the member in that particular team, leading by my professor there. So starting the same with the fundamentals of metamaterials. So here, this particular topic, that is the fundamentals of metamaterial, is going to be interesting for those who want to pursue the research in this particular field. So I am going slightly in a bit more fundamental approach. So here, as far as the introductory part is concerned, that is the introduction of metamaterial. So we are going to say what exactly metamaterial means. If we see the word metamaterial, this is made up of actually two combinations of words. If you see, one is meta and another one is material. So if you look out about this, meta, it's something called as changed, altered, higher, or beyond. In material is your general conventional material, whatever you have. Now, combining both words together, those materials which are altered, which are changed, which are something beyond their existence, those materials we are going to call it as metamaterials. So, again, when the word comes as beyond, what exactly beyond means, that we are going trying to understand exactly. So metamaterials can have their electromagnetic properties that can be altered up to some level, which may not be found in nature as well. For example, they can achieve negative refractive index, negative refraction, zero index of refraction, magnetism at some optical frequencies, and many more such kind of things as well. So, uh, uh, going in a bit more detail, uh, first time Professor Smith, he explained exactly the definition of metamaterial being as any material which is composed of periodic microscopic structures to achieve a desired electromagnetic response. So Professor Smith commented material which composed of periodic macroscopic structures. The definition itself is very broad. So at some instance, researchers have to converge at some particular point to define what exactly this metamaterial is. So other researchers also restrict metamaterial as some approach as uh, engineering approach of material at some subatomic or atomic level, where something is to be done, where people used to alter the properties of metamaterials. But all the researchers definitely agree that metamaterials are they don't have to do anything with the chemical or atomic alterations or properties of the materials. Hence, metamaterials are artificially engineered materials which can modulate the phase and amplitude of the transmitting electromagnetic waves, and that too by controlling the permittivity and permeability of the material. So, how exactly they do this thing? And they do this thing by the fundamental subwavelength structures that they call it as unit cells. And unit cells, they are going to be considered as the main fundamental block for designing of these metamaterials. The unit cell can be placed in periodic, quasi-periodic, or aperiodic arrangement. That may be in a single plane, maybe more than a single plane. That is a three-dimensional structure. Whenever the unit cells are arranged in a single plane, these types of arrangements of unit cells and the material design is going to be called as metasurface. Now, in the same introductory part, there are n number of research, actually many researches in the field of metamaterials are going on, where people are working on antennas, absorbers, metamaterial clocks, metamaterial lenses, and they are not restricted at only these particular topics. Actually, the topic of research in this particular field is going very wide. Now, out of that, let us try to have some of the important properties of these materials. Out of that, the first one here we want to discuss is this backward propagation. As the word itself is self-explanatory, that what exactly, while we are saying backward propagation, what exactly it means. So, before going to this backward propagation, let us consider the phenomena of propagation for our conventional material. Conventional material means this our double positive media, where E and H perpendicular to each other with direction of propagation in also perpendicular to each other. Now, by using Poynting vector equation, H equal to E cross H, all of us well know about this. Now, the thing happens is the wave vector's direction. So when we have double positive media, in this case, the direction of propagation of inertia and the direction of the wave vector both are in the same direction. Now, they are following right hand rule. That's why these materials are also going to be called as right-handed medium or right-handed material. Now, here we are discussing about D and G, double negative materials or medium, let us assume about. So, what kind of differences we are going to observe here is something little bit interesting here. We can observe that in terms of direction of propagation and the wave vector, both are going to be opposite to each other. And that is the interesting phenomena which is associated with the metamaterial. And literally they follow this left-handed thumb rule, and hence these materials are also called as left-handed medium. Now, and this is something called as explanatory way that how backward wave propagation happened. That is just a kind of practical realization. Now, in the same sequence, we have negative refraction. So let us see what negative refraction is. To understand negative refraction, first we are trying to understand the conventional refraction which happens, that is this due to double positive media. So here I have considered air and our conventional medium, double positive medium, for our purpose. For our purpose. Now here what I am going to do is, here I have considered one wave which is incidenting on the surface, and some of the parts of the same waves are reflected in one medium, and another some part of the wave will be propagating into the another medium, and depending on the type of refractive index or the value of the refractive index, they will move towards the normal or they may move away from the normal. And that is just the regular refraction which we know and which we analyze. Now, in the same sequence, what exactly something called as negative refraction? So here we have considered again one media where I have this air, and one interface that is called as double negative media. When we are saying double negative media, what are negative? That is the important thing. What are negative? So material properties, something material properties like permittivity and permeability, actually they are negative. So in this case, if we feel incident on some particular point, some part of the waves will be reflected into the same media, but some part which is going to be transmitted into another medium, that is we are going to call as reflection, happens slightly differently. And this is something called as negative refraction. And why this happens? Because of, again, the main role here is due to backward wave propagations. And that is the realization of negative refraction. And here, in this particular slide, if you can recognize, here I am showing the difference between positive refractive index and negative refraction index. So what happens when the refraction index is positive and what happens when refraction index is negative? The refraction index positive, we all well know and is familiar with all these aspects. But when this is negative, this is the main important characteristic where we have to deal with and where we have to use its characteristic, and we are going to use for various different applications. Again, same phenomena, if we will try to explain little bit in more detail in comparison with both types of materials, double positive and double negative. So this is the conventional refraction which we know. Now, where the change is? Here the change is. That is air and metamaterial interface. And here the component factor and its representation, if you will see again, and that is, you can recognize here the backward wave formation. And this is going to be one of the important property of metamaterial which we will use for various radiators. While saying various radiators means they can be antennas, they can be circuits, they can be several different things as well. Now, as we have seen that during several last slides, I was discussing mainly on permittivity and permeability, and in that also I was discussing about being both values positive, being both values negative. So if we want to do classifications of materials depending on the sign or depending on the values of permittivity and permeability, so here we may have different types of materials classification. One, the first one where both are positive, epsilon and mu both are positive. We call it as double positive materials or double positive media. Now, in this particular case, the conventional propagation, conventional reflection happens. Whenever either one of permittivity or permeability is negative, we call it as single negative material or media. If permittivity is negative, we call it as electrically negative material. If permeability is negative, we call it as magnetically negative material. And that is here, it is something called as SNG, single negative material. And here, in this particular case, evanescent wave formation also happens. The last case, when both of them are negative, epsilon less than 0, mu less than 0, that is both are negative. And here we call it as DNG, double negative material. And here is the most important phenomena which we call as backward wave propagation. Again, taking all these understandings and putting on coordinate systems where taking permittivity and permeability on horizontal and vertical axis respectively, and representing in terms of refractive index. So refractive index that you can give in terms of plus minus epsilon understood permittivity and permeability mu and epsilon. So depending on that, here you can represent when both of them are positive. And when both of them are positive, the conventional propagation, that is standard optical materials. When one of them is negative, evanescent wave formation, that is metals with UV and optical phenomena, natural magnetic materials up to some gigahertz. So this type of distribution and this type of phenomena may happen. And when both of them are negative, that is none other than your metamaterial characteristics. And in this case, here you have the n number of different actually applications, either negative phase, backward wave propagations, negative refractions, and something similar like to that. Especially when both are positive, permittivity and permeability both are positive, there is again one more important reason where refractive index is less than 1. That is also one of the important range or category where people, microwave researchers are much interested in looking. Now, again, putting all our understandings together in terms of applications. So when single negative material, either electrically negative or magnetically negative, then absorption phenomena. When both are positive, positive refractions. When both are negative, negative refractions. So up till now, what I did, I tried to make the clarifications that all types of materials we may not call as metamaterials until unless these materials have this special quality, then only you can call these materials as metamaterials, otherwise not. Now, going to the next, as in previous slides I discussed that metamaterials means permittivity, permeability, both negative. Although I also commented when one of them is negative, they have also its own application, its own characteristics, and that can also be used in various applications. Now, if we consider that how we can generate electrically negative resonance phenomena, or let us think like this. When we are saying that we want permittivity negative, permeability negative, as a designer, question comes how to control permittivity and permeability if I wish to design, if I wish to have negative and positive value. How actually we can design them. So for that purpose, we will have to look for the source or the origin from where permittivity is and from where permeability is. So for that purpose, one of the simplest example, the capacitive phenomena. and the inductive phenomena, that is the coil phenomena. So one of them, if you people memorize or realize, one of them is related to storing of the electric field, and one of them is the magnetic field. And hence, one of them can control permittivity, and one of them can have permeability. And that again comes from practical understanding. So here, when we want to control, when we want to make electrically negative resonance system or some architectures or some structures, then the first time Professor Pendry he did by using copper wire structures, and hence here I have shown in this particular coordinate in by using this copper wire structures. Similarly, to achieve magnetically negative material and magnetically negative resonance, that time Professor Pendry he used split ring, circular split ring resonators. Why actually they have magnetically negative resonance and electrically negative resonance? They are a bit different story, but that can also be well explained depending on the direction of flow of surface currents, field distributions, and something more. Now, as a designer, if designer knows that electrically negative characteristics can be generated by using copper wire structures, and magnetic negative characteristics can be generated by using split ring resonator structures, then if we have to design a media when we need electrically negative and magnetically negative both types of material, then what to do? Take both of the sources and have the designing like this. So take split ring resonators if you wish to design magnetic negative material, and if you want to have electric negative material, take this copper wire structure. And when you want both negative, then take both of the type of structures. And hence, here you have the third one ready, that you are going to call it a DNG, double negative material. And that is the actual source of getting permittivity and permeability negative. So as a researcher, as a designer, this is to our job to verify and satisfy, and to also observe that how we can get this particular phenomena happen. So as far as understandings are concerned, these are the major parts. And as far the applications are concerned, previously also I commented, whenever refractive index is less than 1, that is very, very important for us also. And hence here it is. We can use the same for clocking applications, clocking purpose, like this clock, metamaterial clock. And this clock is for creating invisibility. That is again one of the very, very interesting topic of the research. Now, how metamaterial exactly works, just sometimes earlier I explained. Now, metamaterials have various different applications, ranging from using with antenna, using with absorbers, using with microstrip circuits, with MEMS structures, and with biomedical applications, and many more applications as well. Perfect lens, Pendry's perfect lens. I think now I am trying to go towards the application side of these metamaterials. So Professor J.B. Pendry, he also described the application of perfect lens. A lens where refractive index is -1. If such kind of lenses can be designed, then what uh, what uh, actually what actually the phenomena is going to be if the refractive index is -1? That is again bit more interesting. And here, after the slide, I think I will be explaining the perfect lens phenomena as well. So this is the conventional Snell's law, which all of you know. And here is the professor physicist, Professor Vector Lego, who theoretically introduced the concept of metamaterial first time in 1968. That time people did not recognize how important this particular aspect is going to be. But after 30 years or so, Professor Smith's group in UCST, when he demonstrated first time theoretically that what exactly metamaterials are, from then Till date, metamaterials are getting enormous response from the researchers, and they have n number of applications ranging from microwaves to millimeter waves to terahertz, even further. So these are several applications again, but the historical background, as I told. Now, this is the phenomena which I want to explain for perfect length. So first of all, let us have a look. Okay, so as you can see, what I demonstrated here is I have considered any source, optical source A, and the radiation from them, and we have considered a media where a lens where refractive index is -1, and I have traced the propagation of waves from them. Here you can see the radiations, they are going to the ray trace lines. If you can see, they are going to converge at two particular points, and convergence, divergence, convergence, divergence, similar phenomena is happening simultaneously and continuously, if you will realize. And that is something called perfect lens phenomena. Now, what we as microwave people, what we can understand from this. Let us assume this A as some dipole antenna radiator and a medium with the refractive index -1 placed in front of this particular radiator. And by using this radiator and this media, the convergence of the radiation and convergence of electric field, magnetic field, ultimately convergence of the radiation pattern, that is going to give higher order of antenna characteristic like gain and other characteristics as well. So that's why here this concept Professor Pendry explained at optical frequency, but these concepts are also going to be very, very applicable, very, very useful for microwave people in terms of antenna applications. Now, second question comes, if metamaterials are designed, then how to fabricate them and how to test them about their metamaterial characteristics. There are several methods by which you can do the fabrication process, by using photolithography, the conventional one, and also by using 3D printings. Once they are fabricated, then the question comes how to test them. There are actually two types of testing methods available, resonant and non-resonant. And depending on your structure, depending on your applications, they have again several different types of testing algorithms, testing process, by using waveguide methods, by using free space method. Both of these methods have their own limitations. And again, depending on the applications, we will have to select the type of testing methods. Until unless the testing methods are not satisfying the simulating criteria, the designing of metamaterial structures are nothing but just some kind of frequency selective surfaces, none other than that. So by using these particular methods, we people can have the transmission and reflection coefficients S11, S21, and by using several multiple processes or mathematical extraction techniques, people used to extract permittivity and permeability of the medium. And that is so for our purpose. And once you have the permittivity and permeability, reflective index, we can calculate very easily. These are some of the limitations. Of course, in terms of fabrication, at a higher frequency level, they are a bit problematic. Sometimes the narrow beam bandwidth is also a bit problem, but there are several techniques available nowadays that how we can increase the bandwidth of the operation of metastructures as well. Now, in the second part of the talk, let us go for the future communication and let us see how we can use these metamaterial technologies for our 5G purpose. So when going for this 5G and we calling this as future communication, then question comes at what exactly 5G is. So answer is 5G is of course the fifth generation wireless system. That is one of the next major phase of mobile telecommunication standards. And the scope of 5G will ultimately range from mobile broadband service to next generation automobiles and many more connected devices. The initial 5G new radio specification was completed in 2018. All these are data very well available on the nets, internets, or many more sources. So, as far as customer base is concerned, as a customer, what I need from next generation communication system is uninterrupted high data rate with high accuracy, low latency, high security. As a customer, this is our requirement. Now, as a designer, how we will fulfill these requirements of the customer? Because at a time, we people are the both. That is the designer as well as the user, subscriber, or customer. So, how we can fulfill these requirements? For that purpose, there are several technologies, as I told, where this 5G we are going to use whenever we have enhanced mobile broadband requirements, whenever we have mission critical communications, whenever we have massive IoT applications, we are going to use this. Now, as far as the consumer base is concerned, many data analytics also say that uh, uh, presently about 2.3 GB of data per month subscribers are using, and that will cross more than 11 GB of data per month on their smartphones only up to 2022. So in smartphones only 11 GB data per month. This is not just the data, this is very huge data requirement. So how we can fulfill the requirement of the customer, this is the big problem. Now for that purpose 5G have several arbitrary technologies, something called as low latency, and this low latency maintains actually the high speed and several more things as well. So these are the roadmaps that how 5G is going to propagate internationally by 3GPP standards and community. And for 5G, actually two types of bands are allocated. One we call it as legacy band, and another one we call it as peak data rate band or new band. Legacy band is the sub 6 gigahertz band, which many trials have happened on this particular band. Similarly, at high data rate band, 18 gigahertz, 28 gigahertz, 38 gigahertz, 60 gigahertz, and even now people are also working at 73, 77 gigahertz bands also. And you will be surprised that just a few days back, 5G was tested at for 73.5 gigahertz with a data rate of 140 Gbps, and that was experimentally very well proved. So 140 Gbps of data rate is also possible by using 5G, and that is done on the ground test reality by a Coin company very recently. Now, by this, just I have given you just a small review that what exactly 5G is going to be. So, as antenna designer or microwave people, what we can do for this 5G? And hence here we have 5G millimeter wave antennas. As antenna designer, as microwave people, so here are some of the challenges and some of the circuits, some of the antenna systems which we designed. 5G millimeter wave antennas. So out of that, the first requirement is massive MIMO array for high gain beam forming. And how this beam forming can be achieved. So 5G millimeter wave designs requires massive PMO antenna array with hundreds of antenna elements on the base station. Because the area of an antenna array is reduced because of the frequency, of course, in propagation to the wavelength, an array of millimeter wave frequencies can be up to 100 times smaller than an array for microwave frequency. And that is one of the biggest challenge a designer faces. That's why the concept of this massive MIMO antenna array came. So, in terms of massive MIMO applications, multiple antennas serving to multiple users at a time with multiple inputs and multiple outputs, just in simple words. So here, let us have some look on designing of some antennas, like designing of meta-surface lens for K-band probe antenna. So here, just some of the designs I will be sharing, latest designs which we did, will be sharing with you people. Here on the screen, if you will see some metamaterial structure we have designed with some optimization and realization techniques. Actually, these are one of the standard fundamental structures, one of the circular, modified circular split ring resonators, actually. And by using this, here we have designed the metamaterial structure. If in the second diagram you will see, you will recognize that these structures are having similar dimensions, but actually they are not. They have different dimensions, they have different coordinates, and these dimensions are changed depending on the phase distribution requirement on the surface. And that too, as we did this particular designing for millimeter wave application, here we have this dual pole probe antenna which we designed horizontal and vertical polarized, operating at 28 gigahertz and 38 gigahertz band. Now, after having its analytical analysis with and without meta-surface lens, here what we found that the probe antenna had simulated reflection band from 21.14 gigs to 35 gigahertz. Later on, we also improved its band up to 38 gigahertz also. The probe antenna with meta-surface lens have simulated minus 10 dB reflection coefficient band of about 7 gigahertz as of now. And here we have some of the radiation characteristics, if you will realize, and this is something called the importance of the surface, how the cylindrical waves radiating from the antennas can be converted to the planar one. The simulation part, here you can realize. And here is the phase distribution on the surface due to this, how this perfect wavelet formation happens. Again, these are some of the simulated and measured gains. And here is the fabricated dual pole antenna. This is the fabricated meta-surface lens. Actually, this is a bit different lens. And here is the chamber where we did the testing. And the testing was also one of the excellent one. And here we got a measured gain of about 20 dpi, and that is pretty good for millimeter wave applications. So one of the antenna type is this one. In Korea, with our research team, we also worked on several more 5G planar antennas. Here, if you will see that this one is one of the important 5G millimeter wavelengths which we have designed operating at 5G band, 28 gigahertz band. Parallel to the same one, we have also designed a planar lines with the 5G at 5G frequency itself. And here we have designed a planar lines miniaturize the size of antenna measurement chamber, that is the anechoic chamber size. And this is the major requirement where the project was considered for. Now, in the same series, one of the interesting work which we also did is designing a conical conformer antenna array with high gain and beam switching for 5G application. Here, if you will see, we have 56 wave power dividers which we designed, and 8 different directions of radiations, 1 to 8 multi-stage power divider SMA by using power division topology and all such processes. Here, if you will see on the conformal surface, we have metamaterial cells with different patterning and different structures, if you will realize. And on the back side, the radiating structures are. So they are pretty good for as far as their applications are concerned. And here measured and simulated radiation patterns. That is also pretty good one and very well one. Again, one more work which we did that is pretty similar to Professor Jining Chang's work, which he did by using SIW techniques and SIW technology, that is by using these patches and SIWs. Uh, Professor Jining Chang, he worked the same for 38 and 28 gigahertz band. Here we also did for similar one. Here, if you will see the complete overall antenna setup, the designed antenna has approximately experimentally demonstrated the gain of 28.2 dBi with half power beamwidth of 12.8 degree, low side lobe level that is less than 20.4 dB for the center input port, and the lens antenna features stable radiation over 37 to 38.5 gigahertz. So we have pretty well explanations that how these metamaterials are going to work for millimeter waves and high frequency bands and many more such things. So these are some of the works which experimentally we did and which experimentally we verified in the lab environment as well. And in future also we are trying to work for more higher massive MIMO requirements as per the industry needs. So these are something which we are looking for, that how we are going to connect throughout the world, throughout the locality, all are going to be connected one to one. And that's all from my side. Thank you for listening. Now, all of your questions, comments, and suggestions are available.
Thank you, Professor Amit, for your nice talk and very insightful presentation. So that I hope that many participants have learned many things that we generally missed while we were reading some textbook. So thank you Amit for this. And I would like to request participants to put some questions in the chat box, and I have few more questions. So Amit, Professor Amit,
Yeah, please.
am I audible to you?
Yes, please.
Yeah. So we have a couple of questions in the chat box. So I would like to tell all these questions, and you please kindly reply.
Yeah,
So the
please.
first question is, can we define metamaterial structures without saying epsilon and mu negative at the same time?
No, not at all. Metamaterials are materials only when they have these two as negative. See, other materials which they have is permittivity or permeability negative at once, that is single negative materials. They are also one of the type of the material, but they are not the metamaterial. Again, they have their own important characteristics, and that is also very well used with antenna applications. But we may not call this as metamaterials. Why? Because they have this permittivity and permeability mandatorily should be the negative one, and also they should satisfy the phase requirement conditions. Then only they are going to be called as structures or metamaterials.
Next question is, how the negative index of refraction of metamaterials can be related to physical explanations of gain enhancement of metamaterial antenna.
Yes. we can look into this matter slightly like this. Let us assume if some waves is to be transmitted through some channel, will refractive index is less than 0. That is the negative one. Now think about the waves. Think about the waves which is propagating through that particular medium, and what may happen. As we well know that depending on the refractive index, the waves may move away from the normal and may move towards the normal. That is just if you remember our primary level physics understanding. From there we can predict, we can say. So here also exactly same thing happens when EM wave radiates, and when a medium is with this particular EM wave, which is less than the actual on or less than 0, that is the negative one, then here they also converge in particular direction, and this convergence in particular direction, this enhances the gain itself. So convergence of the EM radiations at some particular point, that gives increase or enhancement in gain.
Okay. So I will move on to the next question. That is how this negative index helps in size reduction of any microwave devices or an antenna.
I could not get
Okay,
it.
I will.
Please.
Okay. Okay. Mm, how this metamaterial structure, which creates negative index, that helps in size reduction. Am I audible to you, Amit?
Just a voice is breaking.
Okay, I am sorry for
Something.
this. So,
Yes.
the question is how this negative index helps in size reduction. Size reduction.
Okay. Okay. Now understood. So people want to ask that how miniaturization and how refractive index negative is important for achieving miniaturization. Am I right?
Yes, correct. Size
Okay.
reduction, correct.
So size reduction is not at all related to negative index of refraction. So size reduction depends on what factor. So for that purpose, maybe people should recognize first that what are the factors on which physical size of antenna depends. And when you will see, you will realize that the equivalent circuit of antenna, patch antenna, which you are designing or which people are designing, that also consists of some R, L, and Cs. So whenever you have RL and Cs connected in some particular manner, depending on what type of patch antenna you design, these structures with equivalent R, L, and C values, they give some proper resonant frequencies. Now, as a microwave designer, we also know to achieve some particular inductance and to achieve some particular capacitance, what will be the value of strip line which we have to design? What will be the value of, let us say, some split ring resonators length and width which we have to design? So, ultimate, my saying here is, depending on how much side reduction you want to do, proper value of inductance and capacitances can be selected, and depending on that, proper order of miniaturization can also be done. For that, You may have to connect some inductance and capacitance in series or shunt with your antenna structures. And that people used to do by using some kind of filtering resonators in top or on the bottom or in series of the antenna itself. But that is nothing to do with an metamaterial or negative refractive index at all. That only have to do with how you can convert your frequency of resonance at some particular f naught by using some proper L and C's value. Hope I am clear.
Uh, Next question to you, Amit, is how challenging is to design a wideband metamaterial?
Yeah,
Any specific
designing of
approach or techniques can you suggest?
yeah designing of wideband metamaterials are really the challenging job. And again, here, actually, the role or the phenomena that how bandwidth widening can be done if is understood at the circuit level, the same can be implemented here itself. So if we recall, the bandwidth is related to resonant frequency f naught and the Q factor of the circuit. Now, if by any means we can do something with this Q factor, depending on you want to reduce your band, you want to enhance your band, you want to get wide band. Ultimately, what you have to do is you have to either increase or decrease the Q factor, keeping resonant frequency same. So now ultimately your job is how we can handle the Q factor. And again, what are the parameters on which Q factor depends on is again inductance, capacitances, and resistance. So ultimately, what you have to do is you have to play with inductance, capacitance, and resistances, nothing else. And by using this, wideband operation can also be maintained very well. Either it is by using some resistive loading or multiple layer structures or whatever they are just the mimic of the same approach which just now I commented about.
Okay. Uh, the next and last question is, could you please suggest any biological applications of 5G millimeter wave antennas?
Yeah. So one of the important biological applications presently is people in UCSC itself. They successfully worked and they demonstrated also that existence of COVID-19 virus by using 5G antenna. Actually, they did microwave imaging at 28 gigahertz. They did not have to anything with 5G as such, but they demonstrated by using 28 gigahertz microwave imaging, COVID-19 virus can also be detected. That is one of the applications. Similarly, there are several more applications like heartbeat monitoring and breathing rate monitoring, BP, sugar level monitoring remotely and without going in direct contact with the patient now. But there are several research in this field are also going on. So already heartbeat detection without going in direct contact with the patient is already achieved at 28 and 38 gigahertz frequency as well. So these are several types of biomedical applications which people are doing and they are succeeding as such.
Thank you, Dr. Amit, for explaining for all these questions. And I would also request at the same time to all the participants for asking all these questions and putting your interest. And also here, I'm not going to take any questions related to software, how to simulate it or how to fabricate it. If you'd like to more details in that, you can directly email to this speaker. He can help you on, or you can consult with some software companies. who is like HFHS or CST directly, so that you can get some answer for your question. So with this, I would like to thank, first of all, Professor Amit for presenting, for giving a nice presentations, and I hope that many participants, including me, are benefited from your talk. With this, I would like to request our chairman of Antenna Propagation Society, Kerala chapter, Professor Abdullah, to say a few words.
Can you hear me?
Yes, sir, we can hear you.
Thank you, Dr. Amit Kumar Singh, for your wonderful presentation. And I really enjoyed. I don't know what about others. And it was very nice. And in fact, today's topic was highly focused and specific, right? And compared to the previous talk, that was a general one regarding antenna, all types of antenna we discussed. This was really interesting and inspiring for the research students. But what I suggest, most of our India, what we lack, the fabrication of these types of antennas, especially 5G and beyond. Most of the research lab in India, except for IITs, they are facing fabrication problem. I don't know what you presented this, Dr. Amit Kumar Singh, is it fabricated in IIT Delhi or the last one or in Korea?
No, no. Whatever 5G applications I did, the previous two I did in South Korea itself.
Yeah.
One actually people are also doing in our IIT Delhi lab also. They are doing.
Okay, fine. That is a thing we face in India. That is a major hurdle that how to overcome, especially when we jump into this 5G beyond and even terahertz antenna. Okay, anyway, thank you for your presentation and this time with these people. And once again, I congratulate and I extend my sincere gratitude. And my thanks goes to Dr. Sugmolde also for arranging and organizing such a beautiful event. And I take this time to all the participants to please kindly attend the third webinar on 30th August, right? I think.
Yes, Professor Abdullah.
At the same time.
Same time.
I invite all the participants, and even then I will send a reminder in the WhatsApp and all. And I thank you for all the participants also. And once again, thank you and have a nice day. Okay.
Okay. So from my side also, thank you, Professor Abdullah, and thank you, Professor Sukumalte, for arranging this talk. And it's really interesting to talk with such exciting and interesting researchers in the field. Thank you, all of you, for listening.
Okay. Thank you.
Thank you, Professor Amit. And also thanks to all participants who presented, as Professor Abdullah just mentioned. And once again, I request you all, your involvement in this webinar series. Please note that it is just a beginning. You will get multiple emails, I think, from Professor Abdullah in next month also. And it will keep on going as much as you can. Every week you will have one presentation like this. So I hope all students will be benefited from that. But the recent one is on 30th of August, same time, and we will keep all presentations at 7:30 either on Saturday or Sunday. So thank you once again to everyone.
Okay, bye.